So in our previous class, we have already discussed about the Maxwell model and Kelvin-Bodic model. So basically in that model, what happens, you are using a dashpot and a spring or dashpot in a series connection or in a parallel connection. And based on this, stress and strains should be calculated or prepared. So basically that two models are Maxwell model and Kelvin model. Now based on this Maxwell model and Kelvin model, as they are comprised of only two components, that models are called two component model. Now in this same type of model, that is model using the spring and dashboard, if you use three components like two springs and one dashboard, or two dashboard one spring, like that, in such cases, this type of models are called three component models. Okay, three component models. Now here details mathematical formulation for the three component model is given. So basically that thing is not needed for you. I just write it for the references only. Okay, for the three component model, see this is a three component model where here one spring and one dashboard is connected by parallel connection, and these both things, basically this particular portion, basically in this model, this particular portion is nothing but your Kelvin-Bodic model, and that Kelvin-Bodic model is connected with a spring in the series connection. Okay, so if you go for the details analysis, so you know what is the stress and strains over there, and after that you just have to consider that stress in that spring in this model. Okay, so basically these are the three component model. Now, after that, one generalized model is there. So, if you increase the number of component, then three component model, four component model. Now, if you increase the component of the model in n numbers, in that case, that type of models are called generalized model. Okay. Now, this expression is basically in generalized models are a large infinite number of components are used. Okay, so instead of two or three components, there are n numbers of components which are used over there. Now, this is an example of generalized Maxwell model. Okay, this is an example of generalized Maxwell model. See here, all these components are connected in series, and after that, all these Maxwell models are connected in parallel connection. So see, this is one Maxwell model, this is another Maxwell model, this is another Maxwell model, and all these Maxwell models are connected in a parallel connection. Okay, so this is a generalized Maxwell model. Similarly, you can design for a generalized Kelvin model, Kelvin-Bodic model, like that. So when n numbers of components are used, in that case, that type of models are called generalized model. And this is your generalized Kelvin-Bodic model. See here, all these are the your Kelvin model where one dashpot and one spring is connected in a parallel connection, and all these Kelvin models are connected with series connection with each other. Okay, and there are n numbers of Kelvin models. So this is basically a generalized Kelvin model. Okay, so basically these are for your basic understanding that what are the different types of models and how these models are formed. These mathematical expressions are not needed for you. You just have to read about that Kelvin and Maxwell model, that is only integrated in your syllabus. Okay, so these are the different type of models and how these models are formed. Okay, this is all about the different types of models and how these different models are formed. Now, let us go for the next thing. Now, the thing is linear viscoelasticity. So what does this mean by linear viscoelasticity? So a rheologic material can be called linear viscoelastic if the following two conditions are satisfied. A rheologic material means that material for which the characteristic changes with the temperatures. This type of materials can be called linear viscoelastic. Linear viscoelastic means their viscoelastic nature is linear in characteristic. Okay, so they could be called linear viscoelastic if these two conditions are satisfied. First one is homogeneity. So for a stress controlled experiment means where stress would be constant, that would be stress controlled experiment. So in the stress controlled experiment, basically that represents the fifth condition. So for a stress controlled experiment, double the strain is observed at a particular time if double the original stress has been applied. Now, for a stress control experiment, double the strain is observed at a particular time if double the original stress has been applied. So basically what happens in a stress control experiment where you can control the stress parameter, in such cases, if you observe a double quantity of the strain, okay, whatever strain should be there, a double quantity of strain, if you are observing for the stresses which would be double of the original stress. So that is homogeneity. Similarly, for a strain control experiment, if that is a strain control experiment, double the stress is observed at a particular time if the double the original strain has been applied. So basically, this is the homogeneity in such cases. So in such case, homogeneity is, suppose there is some stress and strain control experiment. So for a stress control experiment, if you observe a double strain means whatever strain value is there, that is double of the normal strain value. Okay, double the strain values when you are observed at a particular time, and if that double the strain value are observed when the stresses are doubled. Okay, and for a strain control experiment, if you are observing double the stress whenever your strain is doubled, that is called your homogeneity in such case. The next point is superposition. So what is superposition? The response at a given time to a number of individual excitations applied at different times is the sum of the responses that would have occurred by each excitation acting alone at this respective timings. So superposition means the response at a given time. Now, whether that is a stress control or a strain control, whenever if you are applying stresses or you are applying strains, in that case you will get some responses. Now, these responses in a terms of stress or strain at a given time to a number of individual excitations applied at different times. Now, these responses would be different at different time intervals based on the input parameters or and these input parameters or this total response is the sum of the responses or sum of the outcomes that would have occurred by each excitation acting alone at this respective times. So suppose in that case, what happens? Suppose for a stress control or strain control experiments, you are getting different responses for stress and strain behavior. Okay, and this stress and strain behavior at different time intervals are this. Now, if you add up or now, if you go for a individual responses at each and particular time, in that case, that responses for particular time would be supposed like that for each and individual time. And as a total, you are getting a something response of like suppose 20 Newton per mm square for stresses. Now, if you add up all these individual parameters, in that case, that would be equal to 20 Newton per mm square for a system which is superposition. So that is basically the meaning of the superposition in such case. Now, let us discuss what is time temperature superposition. Okay, so in this case, the superposition concept would be more clear to you. Just a minute. So the response of an asphaltic material shows the dependency on time as well as on the temperature. So basically that means the nature or characteristics of the asphaltic material changes along with the time and the temperature on which that material is over there. Now, for example, the variation of creep compliance at different times at two temperatures, suppose T and T double dash, where T temperature T is greater than T double dash, has been plotted schematically in figure 2.16. Okay, so this is the creep compliance of two different asphaltic material at different time intervals are showing over there. Okay, so one is for the T dash, then another one is T double dash, where T dash, the temperature is greater than T double dash. Now, what was the compliance in a creep condition? That is the stress divided by strain is the creep compliance. Now, it can be seen that at a given temperature, suppose T dash, the creep at time T is lower than that of the time T double dash. Now, if you if you can consider this both this time, now see at a particular time T dash, so this is your creep compliance, and at T double dash, this is your creep compliance. Okay. Now, if you find out the time, or if you find out the creep, in that case, you can see that the creep at time t is lower than that of time t double dash. Okay, so that is obvious that the creep of at time t is lower than the creep at time t double dash for a particular t double dash or t dash, whichever you are considering over there. Now, why is this changes? Because as the time increases, the strain keeps on increasing. Okay, as the time increases, the strain keeps on increasing. Further, it can be seen that at given time, say at T dash, the creep at temperature T dash is lower than that of the temperature T dash. This is because if the temperature is higher, the strain will be more at the same given time. So basically, if you consider these two creep compliances, like creep compliance means the stress divided by strain in a creep condition. Okay, in a creep condition, that is the stress divided by strain is your creep compliance. Now here it is representing the creep, and here it is the time in logarithmic scale, that is ln t. Now in this case, if T dash and T double dash represent the creep behavior at two different temperature, T dash and T double dash, where your T dash temperature is greater than T double dash, in that case you can observe some parameters at a given temperature. Suppose T dash, you can observe a creep value of, okay, creep value of suppose C dash creep. Okay, at T double dash temperature, you will observe a creep value of, suppose for that C double dash creep. Now the thing is here, the creep value at T double dash is higher, that is C double dash creep, because as the temperature changes, in that case, strain on these two asphaltic material would be imposing at a higher rate. Therefore, you are getting a greater creep value at the time changes. Okay, or at the temperature at the time changes. So basically, this is the your time temperature superposition. Now, this behavior speaks for an equivalency that may exist between time and temperature. For example, the creep measure at time T at temperature T double dash is equal to C creep. So, for example, this creep, C creep, that is the C creep measured at time T double dash. So basically that are the T dash and T double dash. These are the two time measured at T double dash at temperature T dash. So basically these are the graph for your temperature, and this is the time. So T double dash and this portion, particular portion. So basically that represents the creep of a particular asphaltic material, which is measured at, which is sorry for the interruption. So, which is measured at your time uh, T dash and T double dash with the temperature T dash and T double dash. So, in that case, you can see that what are the creep value at time T dash and temperature T dash, and at time T double dash and temperature T double dash. Okay. Now you can observe that at the same time, okay, at the same time T dash, you are getting the two creep values for different temperature. Okay, so one you creep value for the different temperature for this, and you are getting like C creep value as and C dash creep values. So which are represented by these 2 points. Okay, so basically at the same time you are getting two creep values for the two temperature. Okay. Now similarly, if you draw one particular line, and if you draw this, in that case, you can say that at that particular two different times, your creep value would be similar. Okay, at these two particular different times, your creep value would be similar, but the time is different. So basically, that creep compliance value not only changes with the time, that also changes with the temperature. So basically, temperature and time both plays an important role in that creep behavior of an asphaltic material. Okay, so for this reason, it is called time temperature superposition. Why superposition? Because this time and temperature both are superimposed on that material characteristic, which will enable the material to behave in different way in different time and different temperature. So for this reason, it is called time temperature superposition. So in this reason, for this reason, a relationship between the two time scales can be proposed as your t dash equal to t double dash divided by alpha t. So if you log, take log or ln in this case, in that case it will be ln t dash equal to ln t double dash minus ln alpha t, where t dash can be called the reduced time of t double dash for shifting the test temperature from t dash to t double dash, and alpha t is called the time temperature shift factor. Okay, so in this case, alpha t is called time temperature shift factor, and t dash can be called the reduced time for t double dash. So basically, here t double dash is the higher time and t dash is the lower time. So you can say that initial time is t dash and final time is t double dash, and within this t dash to t double dash time interval, the temperature is going from t double dash to t dash. Okay, so basically for the shifting of the temperature, total time taken is t dash to t double dash, and alpha t basically represents that shifting of the temperature or test temperature, and it is called the time temperature shift factor. So obviously alpha t is a function of these two temperatures, that is, it is function of the t dash and t double dash, capital T dash and t double dash. So one of them can be treated as a standard temperature. So material for which alpha T value is not a dependent of time can be called thermorheologically simple material. So for the material for which alpha T value is dependent on time, that type of materials are called rheological model, and which for which the model for which that alpha T is not dependent on time, that type of model could be called thermorheologically simple material. Now, next portion is fatigue test on bituminous mixes. So, how fatigue test has been done on the bituminous mix? Now, what is fatigue? Fatigue is a phenomenon of fracture under repetitive cyclic or fluctuating load. So basically, fatigue indicates all the different types of repetitive load which causes tensile fractures over the top of the surface. Okay, over the top of the surface, that type of failure of the pavement is called fatigue failure. So in that case, you can see that suppose a pavement structure is there. In that case, suppose that is a vehicle tire, and that would be constantly in contact with that road surface. Suppose that vehicle tire is rotating in a particular direction. So after each and every repetitive load, what will happen in the below portion? There would be some tensile forces which would be acting like that. So because of the tensile forces, this top surface of the pavements have to be, or top surface of the pavements are seen to have formed different crack or failed. Okay, so this failure of the top surface of the pavement because of that repetitive tensile loading conditions are called fatigue failure. Now, the fatigue life of a bituminous mix is defined as the number of repetition for which the initial stress or strain changes by an arbitrary factor. Now, the fatigue life is that it indicates that that how many rotations of a cyclic load can be taken care by a particular pavement. So that indicates by, suppose there are 10,000 rotation, 20 or 20,000 rotation. After that, whatever stress parameter or initial stress or strain of the body was there, that will change considerably. Okay, so basically that is your fatigue life. That is how many rotations of that cyclic load are required to change for the initial stress or strain in a particular body by an arbitrary factor, by a considerable number. So basically that is your fatigue life. So basically that is a fatigue testing of a bituminous material, schematic diagram of a fatigue testing of a bituminous material where loads are applied. Okay, so and this is the depth of that particular specimen, and L is the length of the particular specimen. So loads are applied at a distance of L by 3 in this different positions. So these are the reaction or support conditions of that particular material which you are testing. Now these supports are placed in both the direction because the cyclic loading pushes the beam for the duration of half cycle and then pulls it from the rest half. So see here, supports are placed both at the top and both at the bottom portions of that portion, because whenever you are providing a cyclic loading condition, now by the nature of the cyclic loading condition, for half of the time of that particular revolution, it will push the sample in the downward direction, and for the other remaining time, it will pull the sample in the upward direction. Therefore, you need to provide the support condition both at the top and bottom so that the particular sample remain in its position. So here, figure below also shows two repetitive loads separated by 1/3 of the length of the beam L. So one repetitive load is P and another repetitive load is P, which are acting at a distance of L by 3 of in that sample. Now, why two loads are used? Two loads are generally used because the bending moment in the middle third of the beam is constant and the shear force is zero. Therefore, the failure of the beam takes place on account of the pure flexural fatigue. So, because two loads are taken because the bending moment in the middle third. So, this is the middle third corresponding to this portion, and this is the middle third corresponding to this edge. Now, this bending moment generally at the middle third of the beam is constant. So, bending moment at the middle third is constant, and the shear force, if the bending moment is constant, in that case shear force would be zero. Okay, so therefore failure of the beam takes place on account of the pure flexural fatigue. So there will be nothing, only because of the flexural fatigue only the beam will be failed. So when the beam will be failed, there will not be other consideration like your shear force and bending moment. The beam is failed only because of the pure flexural fatigue. So in this way, you can directly get to the idea of the total fatigue life of the pavement. Now, fatigue tests are generally conducted under two types of control loading, namely control stress amplitude and control strain amplitude. So basically, one condition is your creep condition and another condition is your relaxation condition. So it is sometimes difficult, especially in the controlled strain test, to establish the precise number of repetition required for the failure of the beam. So in the controlled strain test, okay, sometimes researchers are feel that sometimes that establishing the precise number of repetitions required for the failure is very much difficult in the strain control test. So as a consequence, arbitrary definition of the failure condition of a specimens are adopted. So basically, in such cases, in a strain condition, what happens? You will not understand when the particular material failed. Okay, because that to understand whether it is failed or not, that that is very much difficult in a strain condition. Therefore, you need to adopt some failure mechanism so that you can check the total number of repetition in a strain control test. Okay, so as a consequence, the arbitrary definition of the failure condition of a specimen are adopted. For example, 50% reduction in the initial stress may be defined as the failure of the beam in constant strain testing. So in a constant strain testing, what happens? You are constantly straining a particular object. Now, whenever the stress over there is reduced to half of the initial stress, in that case, you will consider that the particular specimen is failed. Now, at that time, whatever number of repetitions are there, that repetition is your total fatigue life or total repetition required for the failure of the pavement. So controlled stress fatigue testing is applicable to thick bituminous layer pavement, while controlled strain fatigue testing is recommended for the thin bituminous pavement. Okay, you can leave the class. I have already taken the attendance.